Hey all, welcome to homeschool. Hope everybody are doing good. And today we are with class 11 chemistry series, the chapter chemical bonding and molecular structure. So we have completed octet rule, its limitations. We learned how to draw dot structure. And we have also studied about bond parameters, right? About bond length, bond angle, bond enthalpy, dipole moment and all that. We also discussed about ionic bond, covalent character in ionic bond and how to decide covalent character with the help of Fazan's rules. All that is over. And today I am with one of the most interesting and important topic of this chapter, that is VSEPR theory. Right? Okay. So the main purpose of VSEPR theory is to predict the shapes of molecules. Especially the covalent molecules do have some shapes. So why do they have shapes? How do they get shapes? How to predict what shape is shown by what compound? All that we will discuss today. First, let us understand the meaning of VSEPR. In short, we will call it as VSEPR theory. Okay, so what is the full form of VSEPR? It is nothing but, valence shell electron pair repulsion theory. Electron pair repulsion theory. So this is what the full form of VSEPR theory, right? Okay. So now the main purpose of this theory, as I already told you, it is to predict what? Shape of molecule. Predict the shapes of molecules. Okay, fine. And now there are certain postulates which you have to learn and analyze point by point. So if you can understand these postulates, you will understand why actually different shapes are possible for molecules. So first and foremost, let us learn about the postulates of VSEPR theory, that is VSEPR theory. Okay, so coming to the first postulate, so I'm writing all the postulates in a very simple language so that you can understand easily. Okay, so the very first point is, this VSEPR theory always depends on, actually according to VSEPR theory, shape always depends on number of lone pairs and bond pairs present on central atom. Okay, see, in every molecule you have something called central atom, right? Okay, so on a central atom you will have some lone pair of electrons and some bond pair of electrons. What do you mean by bond pair? Bond pair is nothing but the number of bonds present around central atom. Okay, so shape always depends on the number of lone pairs and the number of bond pairs. Where are they present? Which are present on central atom of a molecule. Clear? Okay. And shape also depends on, repulsions that existed between these lone pair of electrons and bond pair of electrons. Okay, say for example, imagine if A is a central atom. So on this central atom, suppose you have one lone pair and you have another lone pair and you also have some bonds around it. Okay, so these bonds are with some side atoms. So there are two lone pairs and there are two bond pairs. You will always observe a kind of repulsions between them, because this is a pair of electron, this is a pair of electron, even this is a pair of electron and this is also a pair of electron. So electrons and electrons, when they are near to each other, what happened? You will observe negative forces like repulsion. So two negative charges, when they come close to each other, you will always observe repulsions. Right? Okay. So you will observe such repulsions between these electron pairs. Electron pairs can be present in the form of lone pair or they can be present in the form of bond pair. Okay, so you will definitely observe a sort of repulsions between them. And you know, in any molecule, when you have more repulsions, it will become unstable. So a molecule, if it has to be stable, repulsions have to be minimum. Repulsions between what? Repulsions between these electron pairs have to be minimum. Okay, so shape to some extent depends on repulsions between valence shell electron pairs. Valence shell electron pairs. What do you mean by valence shell electron pairs? It is these lone pairs and bond pairs present around central atom is called valence shell electron pairs. Okay, so that is the reason you can just see the full form of VSEPR, valence shell electron pair repulsion theory. So definitely you will observe a sort of repulsions between lone pair, lone pair, lone pair, bond pair and bond pair, bond pair. So it is these repulsions that have to be minimum in a molecule to have a stable molecule. Okay, so how do you make these repulsions minimum? When do you observe these repulsions minimum? You will observe minimum repulsion in a molecule when they are placed in space, when they are arranged in space as far as possible. Okay, so these lone pairs and bond pairs, whichever are there around central atom, in case if they are far away with each other from one another, if you have nice distance between them, then repulsions can be minimum, right? Only then molecule can be stable, and you know they get arranged themselves. It is the central atom, okay, that actually decides where they have to get arranged. Okay, so central atom is the superhero here. This is the one which thinks, okay, I have these many pairs of around me. They shouldn't be near, because if they are near, there is lots of fighting, right? So to avoid that, I should keep them as far as possible, so that to have minimum repulsion in a molecule. This way the central atom thinks. Because of this, the lone pairs or bond pairs, whichever are present, will stay in a space. They are directed in a space as far as possible. This is what giving a particular shape or geometry for a molecule. Okay, so what I will write my second point here is, you know, the lone pairs or bond pairs, okay, gets arranged in space, okay, in space. So where do they get arranged? They get arranged in space around the central atom. Okay, so they get arranged in space as far as possible. Okay, so there should be a large distance between these bond pairs of electrons and lone pairs of electrons. So why there should be large distance between one another? It is to have, you know, minimum repulsions. Okay, right? So this way the bond pairs and lone pairs arranged in some direction in a space, no, that is responsible for a shape or geometry. Okay, it is because of this arrangement you can observe a particular shape for a molecule. So this is what leads to a shape or geometry. Actually, there is a small difference between the words shape and geometry. I'll tell you what is the difference in the examples. Okay, fine. So these are the two important points of VSEPR theory. Okay, now the third point. I'm talking about the third point. So usually the repulsions between lone pair and lone pair is always maximum than the repulsion between lone pair bond pair, and repulsion between bond pair and bond pair is always minimum. Okay, so this is the strength of repulsions, guys. This sentence is actually very, very important. So when you have two lone pairs on central atom, between the lone pairs you will observe maximum repulsions. Okay, minimum repulsions are observed between the bond pairs. It is always between the bonds. Okay, so this point is really, really important to understand. Coming to the last point, multiple bonds between the atoms. What do you mean by multiple bonds? Double bond or triple bonds are called multiple bonds. So multiple bonds are always considered as single super bonds. Okay, even a multiple bond you will consider as a single bond according to VSEPR theory. For example, I'll tell you. See, you have, let me show it here. You have carbon dioxide molecule. We all know the dot structure of carbon dioxide, right? So this is how we have shown the dot structure of carbon dioxide, Lewis dot structure of carbon dioxide. If I ask you how many lone pairs and bond pairs are there around central atom, what's your answer? Coming to lone pairs. Lone pairs are 0. I'm not talking about lone pairs on side atom. Okay, so here we have to concentrate lone pairs present on central atom. So the number of lone pairs present is 0. And how many bond pairs are there? How many bonds are there around carbon? See here, this side is one double bond, this side is one double bond. You are not supposed to write your answer as 4. See, number of bond pairs is 2. Even if it is a double bond, consider as a super single bond. Even if it is a triple bond, consider that as one bond. So around carbon, actually there are only 2 bond pairs. Remember this. Okay, so this point is also really very important. Whenever you have a double bond or triple bond between the atoms, those bonds consider as single bonds only. Super bonds, strongest single bonds. Okay, so this is the assumptions. This is the assumption that we have to remember in case of VSEPR theory. So I told you 4 postulates here. Always the shape depends on number of lone pairs and bond pair present on central atom, and you will always observe repulsions between these electron pairs. It may be a lone pair or bond pair. Okay, so it is because of these repulsions, what happens? The lone pairs or bond pairs will get arranged in space as far as possible, okay, with maximum distance to have minimum repulsion. It is because of this arrangement in space, they have directed in different direction, isn't it, in space. It is because of this you had got some shape or geometry for a molecule. Okay, and always the repulsions between lone pair and lone pair is maximum than repulsions of lone pair bond pair, and bond pair repulsion is always minimum. Okay, and the last assumption that we have to think over is always consider multiple bonds as single super bonds. Okay, so now we will try to understand the shapes of molecules, different types of molecules based on VSEPR theory. See guys, based on VSEPR theory, all molecules are actually categorized into 2 categories. Okay, so the first category of molecules includes molecules in which central atom has no lone pair. Okay, so whichever the molecules where the central atom, if it do not have a lone pair, then they are categorized as one group. Okay, and another group includes molecules in which, very, very important, in which central atom has lone pair. Central atom has lone pair of electrons. So this is another group. So first and foremost, we will discuss the shapes of molecules in which central atom, Ca in the sense central atom, has no lone pair. Okay, So shapes of such molecules let us try to discuss. Fine? Okay. So in that, the first variety is AB2 type of molecules. Okay, so this is just a general form we have mentioned. So what do you mean by A here? A is some central atom. A is some central atom and B is some side atom. Side atoms. Okay, fine. So A is some central atom and B is some side atom, and A do not have any lone pair. Okay, so that is the first variety. Under this we are going to discuss. Okay, so here we know that lone pair of electrons are 0. Can you tell me how many bond pairs are there? How many side atoms are there? 2. That means there must have been 2 bonds. Yes or no? Between A and B. Right? So even if it is a double bond or triple bond between A and B, you should consider it as single bond only, right? Single super bond. So the number of bond pairs is always equal to the number of side atoms that you have in a molecule. Okay? So bond pairs are 2. So now this A atom, around A, you have 0 lone pair. Lone pairs are not there only. And you have 2 bond pairs. Okay, so imagine I have taken 2 straws here. Say at the center, my finger is the central atom. So this guy is holding how many bonds, guys? This guy is holding 2 bond pairs, right? So how will it arrange these 2 bonds around it? It should arrange in a space in such a way that there should be large distance between each other to have a minimum repulsion. Right? Okay. So, can I arrange the 2 bonds like this around central atom? See, if I arrange like this, the distance is very little, right? So, you will observe more repulsion. So, what happens? I'll just increase the distance. See, I can, yes. So, only possible way I can arrange to have a minimum repulsion is I'll put both bonds opposite to each other, right? So, this is the only possible arrangement for 2 bonds which are there around central atom. Okay, so if they stay opposite to each other, then distance between them is maximum, repulsion is minimum. Then what is the shape you call this as? This is called as linear shape. So if the 2 bond pairs are just opposite to each other, then the shape is a linear shape. Okay, so how do you show? A is the central atom. This side one bond is there with B. This side another bond is there with B. Okay, and this shape is called as linear shape. Okay, or the geometry is linear. Okay, what I can say here? Geometry is linear, or here geometry is equal to shape. Okay. So now I am going to tell you what actually is the difference between geometry and shape. Remember guys, this is really important. So for telling geometry, you should consider both lone pair of electrons and bond pair of electrons. Okay, you should consider total number of electron pairs present around central atom. Okay, it can be lone pair or it can be bond pair. Okay, so a number of lone pairs and bond pairs together will decide the geometry of a molecule. And to talk about a shape, we only consider bond pairs. Okay, we don't consider lone pairs. We only look at the direction of bonds and we decide the shape of a molecule. Whereas to talk about the geometry, we should also consider the lone pairs. Okay, since in this molecule, in this variety, lone pairs are 0, bond pairs are 2. Okay, that is why here shape is similar to geometry. You can call either shape or geometry, that is linear. Okay, geometry is linear and shape is also linear because for shape what do you consider? Only the bonds direction, only the bond pairs. Okay, for geometry what do you consider? both bonds as well as lone pairs if present. But here lone pairs are 0, no, around A, right, in this variety. That is the reason here geometry or shape is one and the same. But if the central metal if the central atom had some lone pair, definitely the shape will be different. And geometry is always decided based on both lone pairs and bond pairs. Okay, on their arrangement we talk about the geometry, but for the shape we only consider the bond pairs. Okay, fine. So hope you got an idea how to differentiate between geometry and shape, right? So this is really important. Anyway, you will understand this in the next category of the examples that we discuss. Okay, fine. But as of now, as long as you restrict your concept to this category of molecules, shape or geometry is same. There's no difference. Okay, so here geometry is linear and shape is also linear only. So what is the angle? Linear shape, if they have, what is the bond angle you will observe? It is 180 degrees. Okay, so can you give me some examples under this model? I mean for this particular formula, examples. Numerous examples are there. One is beryllium chloride, the other one is carbon dioxide. You know, all these are examples for linear geometry. Okay, so this is how you have to identify geometry or shape. So now let us go for the next model, okay, the next variety. If the molecule has a formula of AB3 type, okay. So in AB3 type, can you tell me how many lone pairs are there? Lone pairs are 0 because we are discussing all these under the heading where central atom has 0 lone pairs. Okay, do not have any lone pairs. So lone pairs are 0. So how many bond pairs are there? Bond pairs are 3, isn't it? Okay. So now our central atom has 3 bonds around it. So how do you think it can arrange the 3 bonds around it? So what is the condition? The bonds must be as far as possible. They should be far away with each other to avoid the minimum repulsions, isn't it? So if this my finger is a central atom, then this is holding 3 bonds. How can it hold? Condition is they must stay far away with each other. So what direction they get arranged to stay far away with each other? See, if I arrange the 3 bonds like this, you know, can you avoid repulsions? No, repulsions can be maximum because the distance between the bonds is very much minimum. Isn't it? Okay. So now I will just move on. I'll make it far away, far away, far away. I'll increase the angle and somewhere I get at this point, right? Say this point. And here the angle is 120 degree. Here the angle is 120 and the angle between this straw and this straw is also 120, right? So if I join all these straws, what is the shape you get? You get triangular shape. Okay, so the name of this geometry is trigonal planar. All the 3 bonds are in a same plane. Okay, so it is a triangular shape, trigonal shape. Okay, so how do you show it on a paper or a board? A at the center, one B here, the other B here, and the third B here. Okay, so this is trigonal. And what is the bond angle? Bond angle has to be 120 degree. Okay, so and what is the name of geometry here? Here geometry or shape is one and the same because lone pairs are 0. So here the geometry's name is trigonal planar. Very, very important. Trigonal planar. Okay, so what examples you can observe here? Examples can be BF3, AlCl3, etc. Right? So this is of AB3 type. Now let us go for the third model. If you have a formula of AB4 variety, okay. So in AB4 variety, lone pairs are 0. Bond pairs are how many? There are 4 bond pairs, 4 side atoms. So there must have been 4 bonds between A and B's. Okay, so if the central atom has to hold 4 bond pairs, Okay, so if there are 4 bonds around the central atom, how will it hold? The only condition is these bonds must stay as far as possible, isn't it? So in what direction all these bonds gets arranged to stay as far as possible? Yes, I'll just see how I will move. Something like this, right? And what is this called? Say for example, if I join this with this with this, and at the bottom if I give triangular platform, what shape do you call this as? I join this straw with this with this with this. So at the bottom I join all the 3. So it makes a triangular platform. So the shape is tetrahedral. Okay, and the angle between the two bonds is 109.5 degrees. Okay, so angle between these 2 straws is also 109.5. Angle between these 2 is also 109.5. Angle between this and this is also 109.5. Okay, so this bond angle is possible for tetrahedron. Okay, so the shape here is tetrahedral, or the geometry here is tetrahedral. Okay, very, very important model, right? So how do you show it? A at the center, 1 B here, another B here, third B, fourth B. So this is the tetrahedral shape. So what is the bond angle? 109.5 degrees. So what is the name of geometry that you will tell? Geometry is tetrahedral. Okay, shape is also tetrahedral. So the best examples for this variety is CH4, CCl4, SiCl4, etc. Okay, so whenever you have 0 lone pairs and 4 bond pairs, shape is always tetrahedral. Okay, so they will get arranged as far as possible with the bond angle 109.5 degree. Okay, if they can arranged in this pattern, repulsions can be minimum. So the geometry shown by such molecules is tetrahedral. Okay, fine. So now let us go for next type of molecule. See, our next type is AB5 type of molecule. So in AB5 type of molecule, lone pairs, let it be 0, and how many bond pairs? 5 side atoms. So number of bonds have to be 5, isn't it? So 5 bond pairs are there. So if the central atom have to hold 5 bonds around it, so how will it hold those 5 bonds in a space so that there should be a maximum distance between each other? You observe, among the 5 bonds, I can arrange 3 bonds in a trigonal planar form, right? So this makes a trigonal planar, right? Among the 5 bonds, 3 bonds I can arrange like this, and 1 bond in front and the other bond backside. Okay, so hope you can make out the difference. So green color straws are making a triangle, and 1 pink straw above the plane, the other pink straw below the plane. Okay, this is out of the plane, and the other pink straw is also out of the plane. Okay, and this is the shape they make. What do you call this geometry as? If you join the 3 green straws, it makes a triangle. And you observe these 2 green straws and 1 pink straw. This is 1 green straw, this is 2nd green straw, and this is 1 pink straw. What shape does it has? Pyramidal, right? Something like this, pyramidal shape. This shape is called what? Pyramidal, right? So this is 1 pyramidal shape. Okay, front side 1 pyramidal shape. Back side also, you see, this pink straw and these 2 green straws, if I consider, this makes another pyramid, and these 2 green and this 1 pink, this makes another pyramid. This is 1 pyramid and this is another pyramid. 1 pyramid, another pyramid. Okay, so in the middle you have triangular and 1 pyramid outside, 1 pyramid backside. Okay, so this shape is called trigonal bipyramidal. Okay, so what is the geometry? How do I write on a board? A at the center. So you have one B here, the other B here, third B here. So this makes what, guys? So this makes a triangle, and fourth B is here and fifth B is here, right? So this is how you will draw it on a board or a paper, okay, 2D picture. So here, what is the geometry, name of a geometry? What do you call it as? Trigonal bipyramidal. Okay, let me write it here. Bipyramidal, right? Very, very important type. Okay, so now can you decide the bond angle here? See, what is the bond angle between this bond and this bond? I mean, see, the three green straws are triangular. They are in the shape of a triangle. So what may be the bond angle between two green straws? Any two green straws. The bond angle is 120 degree because they are in a shape of triangle. And what is the bond angle between green straw and a pink straw? So what is their position? You see, you take any green straw, okay, green straw and this pink straw. So how they are? How are they? They are perpendicular to each other, no? You can take any green straw and any pink straw, guys. You see their positions. They are perpendicular to each other. That means the bond angle between this bond and this bond is always 90 degree, right? So there are two bond angles that you are going to observe in a molecule. One is 120 degree, the other one is 90 degrees. Okay, clear? That means the bond angle between the green bonds, okay, triangular bonds is 120, and the bond angle between one green bond and pink bond is how much? They both are perpendicular to each other, no? So the bond angle have to be 90 degree. So that way you will observe two bond angles. Okay, so what is the best example for this case? Best example is PCl5. Okay, so that is about AB5 type of molecule. Now coming to AB6 type of a molecule. So this is also very interesting shape, guys. So fifth type, AB6 type of a molecule. Okay, so here lone pairs are 0 and bond pairs are actually 6. So if you have a 6 bonds, how do you think they get arranged in space? Okay, so just try to observe here, carefully try to observe. Let me try to show it with these 6 straws here. Okay, so among the 6 straws, you see, 4 straws I will arrange in the shape of a square. Okay, like this. Yes, this is, if you join these green straws, if I join these green straws, you know, it becomes a square, right? It becomes a square. Yes, I'm joining 4 green straws, 4 bonds. These are the 4 bonds and I'm getting a shape of square. Among the 6 bonds, 4 bonds I arranged it in the shape of a square. Say if I actually join this green color straws, it becomes a square, right? Okay, and now you see the 5th bond is above the plane of a square and 6th bond is below the plane of a square, right? So this is what the shape of octahedron. So usually what do you mean by the word octa? It is 8. Octahedron always has 8 sides. So how does this has 8 sides? You see, if I join this pink straw with this green straw, one side, this with this, second side, this with this, third side, this with this, fourth side. And at the same time, you know, similarly, bottom one pink straw is there. This if I join it with this, you know, 5th side, this with this, 6th side, this with this, 7th side, this with this, 8th side. So just visualize 3-dimensionally all sides I have joined, you know, it becomes 8-sided structure, which we will call it as octahedron. Okay, so what is the shape of a molecule? It is octahedron. So how do you draw it on a board? So A at the center, So this is 1B. Yes or no? So this is 1B. This is another B. Third B. Fourth B. And 1B above the plane of a square, the other B below the plane of the square. Okay, so this is how we will show octahedral geometry. Okay, now the question mark is predicting the bond angle. You see here, what is the bond angle between green color straws? Bond angle between this and this, both are perpendicular, right? So 90 degree. Okay, so what is the bond angle between pink straw and any green straw? This and this is perpendicular, this and this is perpendicular, this and this is perpendicular. So all green straws are perpendicular to the pink straw. So what may be its bond angle? Bond angle is 90 degree. So here the bond angle between any two bonds is actually 90 degrees. Okay, so 90 degrees is the bond angle. Right? Hope you got clear with octahedral structure. Okay, so this is what we call octahedral. 4 bonds in the shape of a square, 4 bonds in the shape of a square. One bond is above the plane of square, other bond is below the plane of square. Okay, so here every bond angle is actually 90 degrees. Okay, so this is what we call it as octahedral geometry. So what is the geometry here? Octahedral. Okay, geometry which was equal to the shape in this case. And the best example for this category is SF6 molecule. SF6 molecule. Okay, so these are the different, examples or the different varieties under which heading? Under the molecules where central atom do not have lone pairs. In any of these, you will not observe any lone pairs, right? Only bond pairs are there. So always remember, geometry is nothing but, it is, geometry is decided based on the orientation of both lone pairs and bond pairs. Okay, and shape is always decided only based on the bond pairs arrangement. Okay, since here the lone pairs are 0, the geometry was equal to shape. Okay, so both geometry and shape has a common meaning here. So now we will go for the other section of a molecules where we have lone pairs. So if there were lone pairs, imagine if there were a lone pair, if I replace one of the bond with lone pair, definitely this will disturb the geometry. Geometry has to be octahedral, but the shape will be something else. Because of this lone pair, you would observe more repulsion between this lone pair and this bond pair, this lone pair and this bond pair. So the bonds, instead of here, it will move somewhere here. Even this bond, instead of here, it would move somewhere here. Okay, so the shape will be different. Geometry may be same, octahedral, because geometry is always decided based on number of lone pairs and bond pairs. So lone pairs and bond pairs together is 6. So geometry is octahedral, but shape will never be octahedral. For shape, we will not consider this lone pair. And at the same time, the bonds would have moved somewhere far, right? So the shape, for the shape, we only consider these bonds. 1, 2, 3, 4, 5 bonds. So the shape of these bonds will be the shape of a molecule. Okay, so this is how there is a difference between geometry and shape. So this difference we can clearly make out in the next coming examples. See guys, under shapes of molecules in which central metal atom has lone pair, right? So now we are going to discuss the shape of a molecule when lone pairs are there. I already told you lone pairs will disturb the shape. So just observe how it disturbs. So let me consider the first case, A, B to E. So what is A here? Some central atom. Some central atom. And what is B? Side atom. B is side atom. And E is nothing but lone pair. Okay. So here in this molecule, how many lone pairs are there? Just one lone pair. And how many bond pairs are there? it is equal to the number of side atoms, right? So there are 2 side atoms, so the number of bond pairs are 2. Altogether, how many you have? 3, right? So you have 3 electron pairs, isn't it? So when you have 3 electron pairs, logically you should have a geometry. So the geometry of this molecule is no doubt it is trigonal planar. Trigonal planar, right? So always remember, whenever you have like 2 electron pairs, the geometry is linear. And whenever you have 3 electron pairs, you may have only 3 bond pairs around central atom with 0 lone pair, or lone pair plus bond pairs together you may have 3. Okay, then the geometry is always trigonal planar, right? Okay, so whenever you have 4 electron pairs around central atom, both bond pairs or lone pairs together, when you have 4, then the shape, then the geometry is always tetrahedral. When you have 5 electron pairs around, the geometry is trigonal bipyramidal. When you have 6 electron pairs around, the geometry is octahedral. This is the one we have just now we have discussed. Okay, fine. So now, actually speaking, geometry to decide, you must consider both lone pair and bond pair, I said. So when you considered, you got 3. If you have 3 electron pairs, the geometry is trigonal planar. But it is because of one lone pair. See here, this is A, central atom. This is one side atom B, second side atom B, and the lone pair, imagine it is present here. Okay, because of this lone pair, you will observe more repulsion between this lone pair and this bond pair, and you also observe more repulsion between this lone pair and this bond pair. As a result of this bond which was here slightly moved somewhere here, and even this bond which was here slightly will move somewhere here because of the repulsion. I can show this with the help of straws also. Observe. So this is one bond pair, the other bond pair, and here is you have lone pair. The pink color straw is the lone pair. Okay. So there is lots of fighting between this and this. We know lone pair bond pair repulsions are maximum than bond pair repulsion, isn't it? So as a result of this, as a result of fighting between this pink straw and this green straw will move something like this. And there is a fighting between this pink and this green too. So this green also will move something like this. So now what is the shape? Say for shape I told you don't consider lone pair. Only consider bond pair. So in what shape the bonds existed? V shape or bent shape, isn't it? So here the shape is bent shape or V shape. Okay, so that is the shape of a molecule. Understood? For a shape, you must consider only the bonds. And for geometry, you should consider both lone pair and bond pairs. Okay, so both lone pair and bond pairs together, you got 3 electron pairs. 3 electron pairs in the sense geometry is trigonal planar, whereas shape is bent shape or V shape. Okay, so the best example in this case is ozone, right? So if you could remember the dot structure of ozone, how did you write? O, double bond O with 2 lone pairs, single bond O with 3 lone pairs, and there is 1 lone pair on central atom. So central atom has 1 lone pair and 2 bond pair. Double bond you will consider as single super single bond, right? Super single bond. So this is 1 bond pair, this is 1 bond pair. Bond pairs are 2, lone pairs are 1. So in that case, what will be the shape? Shape is bent shape. But what is the geometry? For geometry, you have to consider both lone pair and bond pairs together. That is 3. So geometry is trigonal planar, but shape is different. Because of this lone pair interference, the bonds have slightly moved near and the shape has become bent shape or V shape. Okay, so this is how the lone pairs actually affect the shape. Okay, fine. So now let me go for the second type of a molecule. In case if you have AB3E type of a molecule. Okay, so in AB3E type of a molecule, can you tell me how many lone pair? Lone pairs are 1, bond pairs are 3. Okay, so add both lone pairs and bond pairs, you will get 4. So when you have 4 electron pairs around central atom, 4 electron pairs around central atom, what is the geometry? So here geometry is tetrahedral, no doubt. Geometry is tetrahedral. Okay, but what about the shape? Shape will be different, right? So how do you show the shape? One bond here, second bond pair here, third bond pair here. So here you will show a lone pair, right? Okay, so I can show it with these straws for you. So actually, the 3 bond pairs are something like this, right? Okay, and this is one lone pair. Because of this lone pair, there is a fighting between this and this. There is a fighting between this and this green straw also. So as a result of this, the bonds would move slightly near. So now for a shape, you will not consider lone pair, right? I'll take out the lone pair. So what is the shape now? What is this shape you will call? Pyramidal shape. Okay, so you will observe shape of a pyramid here. So this is a pyramidal shape. Okay, so with the bond angle 107 degree. Normally it has to be tetrahedral, but since this lone pair is there, more repulsion you will observe between this lone pair and this bond pair, this lone pair and this bond pair also. So the shape is something else. What is that something else? It is pyramidal. So what I can write here? Shape is pyramidal. Shape is pyramidal. Okay, so this is how you have to mention. And what example you can give here? NH3, right? NH3, central atom nitrogen, which has got 1 lone pair and 3 bond pairs. So whenever you have 1 lone pair and 3 bond pairs, shape is always pyramidal. But what about the geometry? Geometry is tetrahedral only. So theoretically speaking, the geometry have to be tetrahedral. It is tetrahedral. Because of this lone pair, because of the repulsion between lone pair and bond pairs, shape is changing. It is changing into pyramidal shape. Clear? Fine. Now let us discuss about the third model in this category, that is AB2E2 type of a molecule. So in AB2E2 type of a molecule, number of lone pairs E2, E means lone pair, right? Number of lone pairs is 2 and number of bond pairs is 2. Okay, so all together you will get 4. So when you have 4 electron pairs around central atom, so what is the geometry? G in the sense geometry. Geometry have to be tetrahedral. But what will be the shape? You see here. If this is the central atom A and this is one side atom B, another side atom B, and here you have one lone pair and here you have another lone pair. For shape, you will consider only bond pairs, right? So only this much you will consider. So what is the shape? In what way these two bonds are there around central atom? It is a shape of V, right? Bent shape, where the bond angle here is 104 degrees. Okay, because of this lone pair repulsion and lone pair bond pair repulsion, bonds would slightly move. Okay, you see here. So these are the 2 lone pairs and these are the 2 bond pairs, right? This is one lone pair, another lone pair, bond pair. There is a repulsion between this and this, so this would move like this. And there is a repulsion between this and this also. So this green bond, this is a bond pair which is moving like this. There is a repulsion between this and this also. So this bond also would move. So now for a shape, we don't include lone pairs. So now what is the shape? Okay, central atom is here. So this is one bond pair, this is one bond pair. So the shape is V shape. So shape that you get here is V shape. Okay, so the best example here is H2O. Okay, so here oxygen is the central atom where it has got 2 lone pair of electrons and 2 bond pair of electrons. So any molecule with 2 lone pairs and 2 bond pairs, shape is always V shape or bent shape. Okay, let's go for the next type. See, our next type is AB4E type. Okay, so here you have number of lone pairs as 1 and how many bond pairs are there? 4 side atoms, so bond pairs are 4. So altogether 5 electron pairs are there. So if you have 5 electron pairs, around the central atom, what is the geometry? Geometry is trigonal, bipyramidal. Okay, so that is what the shape you will have. So how do you arrange that? A is here. You all very well know that trigonal bipyramidal, in the sense this is how the 5 electron pairs are arranged. Okay, so here is 1b, here is 1b, here is 1b, here is 1b, and the best possible direction I can show lone pair is here. So here there is a lone pair. You can't have lone pair here or here because more repulsions you would observe. You will observe repulsions with more bonds. So if the lone pair is here, you have, this is one repulsion you will observe. With this bond, another repulsion you will observe. With other two bonds, there are no much repulsions, right? Okay. So now what is the shape? So for telling a shape, what did I tell you? For telling a shape, we don't consider, this lone pair, right? So now what is this shape? Imagine, see here. So this is, see guys, this is one bond pair, another bond pair. Okay, so third bond pair is something like this. Oh, okay. And fourth bond pair is something like this. Okay, so here the lone pair of electrons are there. You can see my green chalk pencil. This is lone pair. Lone pair I shouldn't consider for telling a shape. So now what is the shape? This looks like a seesaw, right? It just looks like as if the two guys are playing seesaw. You must have seen seesaw at schools, right? So this is the shape of seesaw. So this moves, a boy moving like this, right? When a boy moves like this boy will come up, right? So it is a shape of seesaw. So what is the shape I can write? Seesaw. Very, very important type. Okay. So the best example for this case is SF4. So SF4 is a molecule. The central atom is S. It has one lone pair of electrons and 4 bond pairs. Clear? And let's go for next model now. See, our next model is AB3E2 type. Okay. So here you have lone pair of electrons 2, bond pair of electrons 3. So altogether 5. So theoretically speaking, 5 electron pairs are there around central atom. So what should be the geometry? Geometry is same, trigonal bipyramidal, right? But what will be the shape? Where do you arrange the lone pair of electrons? So if A is the central atom, this is how the 5 bonds are located around central atom, right? Say here I'll put one B side atom, another side atom, third side atom. So this is the position occupied by lone pair. These positions are called equatorial position. Okay, triangle positions are there. No, this and this positions are called equatorial position. And above the plane one bond, below the plane one bond. These positions are called axial position. Okay, so lone pairs always occupy equatorial position. Only then repulsions are minimum in a molecule. Okay, so now can you tell me what is the shape here? Just neglect the lone pairs, only observe the bond pairs. So it is in a shape of T, right? So the shape here is T shape. Molecule will show T shape. Okay, so the best example is ClF3. So Cl is the central atom. 3 fluorine atoms are arranged in the place of B. And there are 2 lone pairs on Cl. They are arranged in equatorial positions. Okay, so this is one of the very, very important example. So molecule of this type will always have what shape? T shape, because 2 lone pairs occupy equatorial position, not the axial position. If they occupy equatorial positions only, repulsions can be minimum. Clear? Fine. Let's go for next variety. See, we have a variety AB5E. Okay, so in AB5E, number of lone pairs is 1, number of bond pairs is 5. Altogether we have got 6. So if you get a number 6, if you have 6 electron pairs around central atom, what is the geometry? Geometry is octahedral. Yes or no? Geometry is octahedral. But shape will be different because of the presence of lone pair. So how do you show the octahedral geometry around central atom? This is how you will show octahedral geometry, right? So here the 4 bonds which looks like a square, right? The 4 bonds, if I join, I get a square, right? So these positions are occupied by the side atoms, and the one bond is above the plane, the other bond is below the plane, right? One bond above the plane will have one side atom, and here occupies a lone pair. Okay, lone pair is present here. Okay, then you would observe minimum repulsions in a molecule. So now neglect the lone pair. What is the shape you can give? So this is a square and this is a pyramidal, right? Above a pyramid shape is there. So the shape is square pyramidal. Square pyramidal. Okay, this is called square pyramidal. So the best example for this case is BRF5. This is also one of the very important example. So it has got 5 side atoms, okay, and 1 lone pair. Br has got 1 lone pair and 5 bond pairs. So the shape is square pyramidal. But what is the geometry? Geometry is octahedral. Okay, so this lone pair disturbs the geometry, it changes the shape, and the shape is square pyramidal, right? So these are the different important models that you need to remember in case of molecules which do contain lone pair of electrons. Okay, so this is what we mean by VSEPR theory. So this is how, based on VSEPR theory, we can predict the shapes of molecule. Okay, so one of the very important topic for the competitive examination. Do concentrate, learn each and every model perfectly with a shape and geometry. Clear? Fine. So that is all about today's video, guys. So in my next video, I will come up with the next theory, that is valence bond theory. Okay, and later hybridization. Thank you so much. Do subscribe our channel to learn the concepts in an easiest way. See you all in the next video.